Good evening, everyone. It's my pleasure to welcome you all to the VLSI Design Time Beginner's Guide to Verilog session, hosted by IEEE Scala Chapter in collaboration with IEEE LBS ICW. Today, we have the privilege of being joined by our esteemed guest speaker, Mr. Sangeet, an FGPA engineer at Tejas Networks with an MTech in VLSI Design. Without further delay, I'd like to invite Mr. Sangeet to take the stage and share his valuable insights on VLSI design from concepts to product. Let's give him a warm welcome and get started with the session.
Yeah. So good evening all. The industry that working in VLSI design as well as Verilog, like whatever companies are there in semiconductor sector, one part of that company will be a design part. So for the design section, we will be using one HDL language. It will be either system Verilog or VHDL, anything. Whatever HDL languages are there, one of them will be used. So the most common Verilog. In my company also, we are using Verilog. So I will start to share the screen. Wait. Screen visible, right?
Yes, sir.
Okay. Okay. Why we need HDL? HDL. So you guys know, like in our phones or laptop or any electronics equipment we have a chip inside that. In that chip, it contains around millions of logical gates, memory elements. So many things are there. So to design that in what connecting that pin to pin, it will be a difficult and error-prone procedures. So if someone is chatting, I don't be able to see that. Okay. If something comes up, coordinators let me know.
Sure, sir.
So uh, for designing a CPU or any basically any chip, billions of logical gates are there. So to design that in an accurate way, we can use this HDL. So that is the basic use of this HDL actually. So we will be having different kind of HDL. We have Verilog, we have then system Verilog, we have then VHDL, we have. And nowadays, people are using some other languages also like BSP, then C related Verilog is there, E related Verilog is there. So we in this workshop we will be basically dealing with this part only. So we will be designing a digital circuit in coded manner, and we will be seeing of that through simulation. Okay. I will be giving you all the basics what you guys will be needing while you are dealing with Verilog. That's the only time we have. Okay. So all this introduction, why we need VHDL, what is the use of uh, this VHDL, then uh, introduction to VLSI, then the steps, design flow of the VLSI. These all things are available in everywhere. You can search that. I don't want to spend more time on this introduction part. I just want to give you an overview uh, of the Verilog coding style. Just I will write one code now and I will explain that. This is the simple Verilog code. So you guys can see one keyword, all the keywords I will list down here. So we have module, that is one keyword. Then we have input, then output, assign, then end module. End module have don't not have any space. It's one word, okay? So Verilog is case sensitive, so you have to be careful while dealing with case sensitive coding style. Okay, so we will be starting our entire design using the keyword known as module. So this HA is module name, that is user defined. So I'm giving HA means half adder. So this. So to create a NAND gate, we will be using this or this. For NOR gate, we will be using this or this. Okay. So here I am done. Assign is a keyword. Basically, it is assigning our sum as A XOR B and carry as A and B. This is basically uh, designing an half adder. Okay. In this, you need to be careful when we are defining an ports, that port should be proper. Whenever we are defining a output port in input port, then the functionality will be different. It will be showing some other errors, or when we are means simulating the setup, we will be getting some other functionalities. So it will show some errors. So that you need to take care. All the ports that need to be properly labeled. What ports are we are using? If internal ports are there, that will be separately given. That we will discuss when we are dealing with full ladder or some other circuits. Okay, then for every module, to end that module, we will be using end module. In between, if you guys have any doubts, you can directly unmute and ask, or you can put that in chat. I will deal. Okay, so this is the basic Verilog code. Any doubt in this?
Hello. Hello.
ഇതൊന്നുകൂടെ പറയാവോ?
Sorry, your voice is. Sorry.
ഹലോ, കേക്കാവോ?
പറ.
അല്ല, ഇതൊന്നുകൂടെ പറയാവോ? എനിക്ക് ഇതിനെപ്പറ്റി ബേസിക്സ് ഐഡിയ കുറവത്രേ.
You know the digital electronics basic, right?
ഇല്ല, അത്രയ്ക്ക് പരിചയമില്ല.
Okay. So for half adder, we have two inputs and two outputs. Okay. So we will be giving 0, 0, 0, 1, 1, 0, 1, 1. Sum will be 0, 1, 1, 0. Carry will be 0, 0, 0, 1. So after doing the K map and everything, These things we will be dealing in digital electronics. I won't be covering that. So we will be getting S is equal to A XOR B. Or if we are using the same variable, it will be capital, okay? A, B. And carry will be A and B. The same thing, whatever we have designed means it will be like this. This is basically an half adder. Yes? Any doubt in this?
അതൊന്നുകൂടെ പറയുമോ ഡയഗ്രത്തെ വെച്ച്?
I'm not getting what you are not able to understand.
അല്ല ഈ ഗേറ്റ് കൂട്ടുള്ള ഈ ഡയഗ്രം ഇല്ലേ, ഇത് വെച്ച് ഒന്നുകൂടെ പറയാമോ?
Sir, he wants the part from the gate part to be explained once
This
more.
is an XOR gate and this is an AND gate. You know that, right? Which semester are you in?
തേർഡ് സെമസ്റ്റർ സ്റ്റാർട്ട് ചെയ്തു.
You are covering your digital electronics in third.
ഉണ്ട്.
In that you will be dealing all these gates. You will be having OR gate, XOR gate, AND gate. All those gates you will be dealing there. Basically, I just need to give you what we are going to design this digital part. The same you can write in Verilog code. So you don't worry about all these things. These things will be covered. Okay. So when you are studying this digital electronics part, parallelly you try to write the Verilog code for that design. That's the ultimate goal. Understood?
ഓക്കെ
Okay. So
Okay.
I'm just saying that sum will be A XOR of B and carry will be A AND of B. That's the only thing you need to think of this half adder. Okay. From there, we are designing this part. So in a module, I'm naming it as half adder. It contains these ports S, C, A, B. And A, B are our input and S and C are our output. So the functionality we are defining in an assign statement because we are using data flow modeling. So S will be A XOR of B, C will be A and B. So in data flow modeling, we will be dealing with in operators. You have to remember this. Okay. So to end the module, we will be using the keyword end module. So this is the basic Verilog structure. We will be defining our module with the module name and ports and ending that. Inside that, we will be declaring the functionality of the ports and the functionality of this module. Okay.
ഓക്കെ.
Okay. Now we have different styles of modeling. We will be dealing with data flow modeling. Then we have switch level modeling. We have behavioral modeling. We have gate level model. I have intentionally written this in different order than the level of abstraction. So the level of abstraction is something different that I will discuss. Okay. Level of abstraction is different from this kind of list. Okay, it will be starting with switch level, ending with behavior. Behavior is the highest level of abstraction. We will be designing. So digital circuits, I said. Okay. Okay. We are designing digital circuit. We are getting, and we design one half adder in data flow modeling. That also we understood. Now, why we are going for different modeling? We have already designed an half adder in data flow modeling. Then why we are going for different modeling? The same half adder code we can write in gate level modeling. It goes something like this. Okay. So for gate level modeling, we will be using primitive gates. So AND, OR, NAND, NOR, XOR, XNOR, BUF. These all are primitive gates that are available in Verilog library. So with these, we will be designing our circuit. So instead of writing assign S is equal to A XOR B, in gate level modeling, we will be writing like this. We will be calling the XOR primitive gate, and we are calling that gate as X1. And inside the bracket, we are need to write the port. Okay. So the primitive is designed like first port will be output and the other ports will be input. So here S will be our output port, A, B as input port. As the same as our definition here. Similarly, for carry, it should be A and B. So we will be calling to do the AND function, we are calling the AND operator. So the AND gate we are calling from primitive library and calling it as A1. C will be our output, A and B will be our input. To end the module, we are using same end module. So data flow and gate level modeling is kind of similar. Nothing is there. We are instead of using operator, we are calling the gates. So why we are going for these two different models? This gate level modeling, you got an idea? What's the change from the data flow modeling? Okay, I think everyone
Sir,
got.
please explain that once more.
Yeah, tell me.
Please explain that gate level modeling once more.
So in gate level modeling, we will be using the primitive gates. All the primitive gates that are available, I have mentioned here. We have AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, buff gate. These all are there. So with this, we will be designing our functionality of the module. So for half adder, we know we need an XOR gate and an AND gate from this diagram. We need an XOR gate and we need an AND gate. The same I have used here. So for XOR, we will be directly calling XOR. And for the gate, if for an example, if I am saying like we have two XOR in one design. So if you are not mentioning the name that I have mentioned here, like this is X1 or this this is x2. Instead, you are writing only x or s of AB, and let's say this is s and this is z, and this is z of AB. While writing, we know, okay, this is the z part and this is the s part. So for the system, but where the Verilog code is being synthesized, that didn't get which XOR need to be S output and which XOR need to be Z output. That's why we are giving it names. Instance name we say. So you need to give
Okay, that's
this.
clear.
Sorry.
The numbering part is the one that I have doubts. Yes, that's clear.
Yeah. So we will be giving that, and the first should be output always. Okay, you need to take care of that. If you are giving A, B, S, it won't work. It will throw some error. Okay, so primitive every gates first input will be always output and all other will be outputs. Inputs, sorry. Any more doubts here?
No, sir, clear.
Okay. Now I will say why we are going for different model. The thing is, for this half adder, full adder, those are simple circuits. It contain not more than 4 or 5 gates. So what if it contain 100 gates or 1000 gates or 10,000 gates? Every time we need to call these primitive gates and we need to define an output, input, output, input. That is not possible. So whenever we have a simple circuit that contains 2 or 3 gates, that too we know the circuit won't change, like this half adder or uh, like 2x1 mux or decoder or all these combinational circuits, whatever we have dealing with, without having not more than 5 or 6 gates, you can deal with that in gate level modeling. You can directly call the primitive gates and define that. So for 2x1 mux, I am taking it as an example. So for 2x1 mux, we will be having 2 inputs and 1 output and 1 selection line. Right? We will be having A, B, and output I am defining it as out, and selection line I am defining it as S. So if S is equal to 0, we will be getting OS A. And F is equal to 1, we will be getting OS. So this is basically what a mux is doing, right? So if you want to write the truth table of this, it will be like this: A, E, S, O. We will be having 0, 0, 0. So whenever S is 0, we will be getting A, right? So it will be 0, B, A, B, A, B, A, B. Sorry, this is 0. It's correct, right? So after solving this in K-map, we will be getting like O is equal to negation of S and A for S and B. So this will be the Boolean expression. Okay, you can solve that, and you will be solving this in digital electronics. Okay, I want to explain why we are going for different model. So here, when we are using the gate level modeling, we will be having an NOT gate, an AND gate, and an OR gate. Right? We will be using two AND gate. So we will be having total 4 gates you will be needing while dealing with the gate level model. So the same thing you can do in assign equal to S equal to 0 will be A question mark, sorry, A, wait, and then, or it will be B. This is same God. Okay, so this statement, what I've written in gate level modeling, sorry, data flow modeling, sorry, it's using the operator called as operational operator, conditional operator. Okay, the condition here is we are checking whether S is equal to 0. We are getting confusion with O and 0. Okay, I will use some other variable like Z I am using. Okay. So it's checking whether S is equal to 0. This is equality operation. When we are using 1 equal to, it will be either assigned statement or blocking, non-blocking, that we will be discussing in behavioral modeling. Then we will get to know. And when we are using 2 equal to operator, this is equality operator. So whether it is checking LHS is same as RHS. So here S is checking whether it is equal to our no, say it's equal to 0. So if S is equal to 0, we are giving Z as A. So the first thing argument will be true and the second will be false. So whenever A is not equal to 0, it will be giving B to Z. Whenever it is equal to 0, it will be giving A to Z. So while designing 2 cross 1, we will be needing 4 gates for gate level modeling. So think of 8 cross 1 mux. We will be having 3 selection lines there. We will be having 8 inputs there. We will be having 1 output there. It's a long Boolean expression when we are solving that. So while dealing with that in gate level modeling, you will be requiring more than 16 to 18 gates. So when we are dealing that in data flow modeling, you can use this conditional operator, or you can even, if you don't know how to use the conditional operator when you are solving the Boolean expression, not the optimized one, even if you are writing something like in this expression itself, if we are expanding that, the expanded version will be a lengthier one, right? So that expression itself you can use in data flow modeling with operators. You are getting it, or should I explain with an example?
Sir, please explain with the example.
So the same 2 cross 1 marks I will write in gate level modeling. So the first thing we need to create one NOT gate of S. So this will be S bar, and we are storing that in known as S underscore bar. So we have a wire known as S bar. I will explain what is wire. So we will be having an NOT gate A1, and output will be S bar, input will be S. Then we need an AND gate A2, and that we need to define like the first part of this we need to store it, right? So we will be having, I am calling it as X1. So it is in another wire X1. And the second part is also need to be stored in some variable. So that is X2. Okay. So our first part of this, we are storing it in X1, and we are using S bar and A as our input. And the second part also need an AND gate A3, and that we are storing in X2 as input as S and B, right? And these X1 and X2 need to be ORed and stored in Z. So A4, Z will be our output, X1, X2 as inputs. And okay. So in a design, if there is interconnects, like this is part A of the design where this is happening, that I am calling it as X1, and this part is happening, called it as X2, and the signal that I have already defined, like when S is converting to S bar, that we are storing in S bar. So whenever we need to store something intermediate values, it won't be like treating it as a memory. It will be interconnect like a wire. Like if you want to, I will explain this. Okay. So we have one more block here, and this is our S. So this is S bar. This is what this is doing, like it is converting this S into S bar, and this S bar we are using in this X1. So in between it's doing some operation, and it is converting that into our required thing and connecting here, right? So that interconnect, what we have to do, that will be stored in wire. Even if we are not storing, like declaring it as wire S bar, wire X1, X2, and if we are using that in the code, like without declaring this, let's say I am not defining this X2, I have defined only X1, and still in the code I am using X2. So the Verilog coding, it will be treating it as a wire. By default, it will be wire. There are other parameters like regs also. We have wire and regs. This treating it as an interconnect, it won't store anything, but this is as act as a memory. It will store the value. Okay, this reg part will be more useful when we are dealing with sequential circuits. Combinational doesn't have any memory element, right? So those all things we need only interconnect. First of half of the Verilog, what we are dealing in this workshop, we will be dealing the combinational part only. Then we will be going to sequential part. At that time, we will be more using this reg part. So for right now, we will be using only wire. Treat it as an interconnect. Okay, whenever we need to store an intermediate something, we need to interconnect, then we need to use that variable. Okay, So this is how this 2x1 mux is designed in gate level modeling. Any doubt in this?
Yeah, now it's clear.
Okay. So the same thing I am writing in data flow mode. Model mux ZSAB input S A it assign. Either you can write directly like this, the Boolean expression with operators, or you can write using conditional operator. This both you can do. Instead of writing how many lines? One, 1, 2, 3, 4, 5 extra lines. We are writing it in a single line. So if you know the Boolean expression, go with data flow modeling. And if you only know what all gates are using and what all the inputs and outputs are connected, interconnected, and those digital diagram, what is it? Gate level diagram you have, then you go with gate level model. So if you are not able to solve the entire circuit, when we are dealing with hundreds of gates, when we are not able to solve that, you can go with gate level modeling. And if you have the condition, like whenever this happens, this should be output. This condition like of statements are mentioned in the design, then you can go with data flow model. And the next modeling is behavioral modeling. Behavioral is just like writing the truth table, same it as. So we will be using like this. But for behavioral modeling, some things are different. I will explain. Okay, this is how we write the code in behavioral modeling. So I will explain. The same module name, ports. We will be defining input ports as A, B, and S. So that all are similar. Whenever we are writing output in behavioral modeling, that should be in reg file. Reg. So if you are not defining, then these A, B, and S are treated as wire. If I am not writing reg, Z also should be wire. But for behavioral modeling, output should be in reg. Okay, that's the first thing. Then what we can say is there is one statement known as always. Always at star. what this means is whenever there is a change in the inputs that we have for input as A, B, and S, right? So whenever it is changing from 0 to 1 or 1 to 0, any of these changing, then this always block whatever begin to end is not what in C++ we use curly brackets, right? The same effect is given by begin and end. So this part will be executed whenever there is a change in this A, B, and S. This asterisk sign is basically mean these all inputs. So instead of writing asterisk sign, you can write also like A, comma, B, comma, S. You can write like this also. So if you want to like ignore the change of S, then you can remove that part in the sensitivity list. So this part of the always block is known as sensitivity list. So whenever this signal is changing, that is sensitive to this always block. That's the thing. Okay. So in the inside that we are using if and else part. If condition we are checking s is equal to 0, then if statement have multiple statements, here also we need to use begin and end. If single line is there, then not required to use, but you can use. Okay. And the else part z equal to b. This is more kind of C kind of style, right? We will be dealing all the combinational and sequential part in behavioral modeling more. And whatever, what do you say, that common digital circuits are there that we will be dealing with data flow. Okay, so we have met with different modeling. In this, we have deal with data flow, behavioral, and gate level. This switch level modeling basically is used for designing CMOS, NMOS, PMOS, those kind of but switch level kind of design. This is not a we can't synthesis it. So for knowledge purpose, you can explore this. We are not going to deal switch level modeling. We will be more dealing with behavioral modeling and data flow modeling. Okay. So you got an overall idea what are the modeling we have, then how we are designing that. This behavioral modeling, you got any doubts in that? You understood sensitivity list?
Yes.
Okay. So I want you to design 4x1 mux using conditional operator, data flow model. Everyone try this and send it in the chat. 4x1 mux. Okay. Gaudi. The thing is, if I'm dealing with digital electronics part also, it will take more time. So for now, you only deal with the syntax and how this all modeling, all these things are working. The digital part you will be dealing in third semester. At that time, you can more focus on the design part.
Okay, sir.
If I'm taking that what two table and solving that in KMAP, it requires at least an half an hour more.
Yeah, yeah. We have sessions tomorrow and the after.
So guys, tonight I think I will explain that 4x1 mux equation or Boolean expression or truth table. Then you guys try to design that. That will be more easy, I guess.
Okay, sir.
So for 4x1 mux, we will be having four inputs. We will be having A, B, C, D. We will be having two selection lines, S1, S2. We are having one output, Z. Okay. S1, S2, Z. If it is 0, 0, we will be giving A. For 0, 1, it will be B. For 1, 0, C. 1, 1, D. This is not exactly the truth table, but this is the functionality table. So according to the selection line, whenever it is 0, 0, then Z will get A, like that. So first we need to check whether S1 is 0. Then inside that you need to check S2. Then you need to provide A or B. And if it is not true, then you need to check again inside that whether it is C or D. Try that and I will explain after you guys. You guys are trying, right? Okay, I will give you till 8:10.
Hello, sir. Are you stuck?
No, no, I'm giving them time. You guys have done? Vaishnav, you have only declared the module. Functionality you have not declared. Also, the semicolon is missing. Okay, I will explain. There are two methods you can do this. So first I will do in simple way. Like I'm not defining anything. I'm directly writing the functionality. Other things you are capable of doing now. This is question mark, okay? So this is one method. So here we are defining all those things, input and output, all those things are there. I am only declaring the same part. Okay. So first we are checking both are zeros. If both are zero, then true will be A, right? That will be given as A. If it is false, then again we are checking whether it is 0 or 1. 0 and 1. If it is true, then we are giving that B. And again we are going for the false part and again checking. Then again checking, giving. This is same as this truth table, right? Or functionality table. This is one method. Any doubt in this?
Hello, sir. Can you hear me?
Hello?
Sir, I've had out.
Yeah, tell me.
Are we using logical or and or bitwise and?
So the thing is, if it is 1 bit, there is no difference between this logical and bitwise. This is bitwise and this is logical. So here we are dealing only with 1 bit of signal. That's why I have not explained this. While dealing with multiple, we are using vector. Then I will explain this. What are the difference between this bitwise and logical? Okay.
Yes.
So either you can use this or this in this. No issue. Because this A and B, C, D all are 1 bit. Either it can have 0 or 1. That's why it is known as 1 bit. Other than any doubts? Okay, next thing you can do is the same thing I am doing in different way. So you can define like I will write the entire code. Module mux instead of writing S1 and S2, I am writing only S. Okay, so I will be defining it as an vector having 2-bit. And other inputs are A and B, C, D. Then output we have Z. So what this means is we have S of 0 and S of 1. This all things is there in C++ and C, I guess. So similar thing only. So if you have 8-bit of data, 8-bit of a signal called as S, then we will be defining it as 7 down to 0 S or 0 down to 7 S. What is the difference between these two is this will be our MSB and this will be our LSB. So the most significant bit and least significant bit. While we are writing, we have a vector path here. Okay. Instead of writing 7, I am taking 4. 1, 2, 3. Okay. So 4-bit I am taking for explaining. So 3 down to 0 we have and 0 down to 3 we have. Right. So the address positions will be like for this 3 down to 0, it will be 3, 2, 1, 0. For 0 down to 3, it will be 0, 1, 2, 3. So if we want to write 8 or 7, 0. Okay, let's see. So I was saying like for 4-bit, how to declare this 4-bit in what is the difference between these two? Okay. So let's talk like we are feeding the value 0, 1, 1, 0 to this 4-bit signal. Okay. So this is 6, right? So the 6 we are giving to this 4-bit. And here the MSB is S of 0. And here the MSB is S of 3. MSB means this value. And LSB means, okay, let's take it as 7. So you understand. So here LSB will be S of 3. And here LSB will be S of 0. That's only difference. You can write either this way or this way. If it is 4-bit, then it should start from 0 to 4 minus 1. If it is 8-bit, start with 0 to 8 minus 1. Like that.
Sir, please explain that last concept.
MSB, LSB.
Yeah.
So we need to write a signal with a value of 6. Or 7 in this case. Okay, 7. When we are converting, it will be 0, 1, 1. Okay. So either we can use 3-bit or we can go for 4-bit. for 7. I am taking it as 4-bit signal. So we will be defining A as 3 down to 0, 8. So in that case, we will be writing 0, 1, 1, 1. So A of 3 will be 0. A of 2 will be 1. Then A of 1 will be 1. A of 0 will be 1. If we are writing 0 down to 3 of A, we will be getting A of 0 as 0, A of 1 as 1, A of 2 as 1, A of 3 as 1. Nothing else. This should be MSB and this will be our LSB.
Okay.
Okay. So coming back to this Mux design, so we have defined S as 2-bit, so 1 down to 0 S. So general practice, whenever we are defining a vector, we will be defining like this instead of 0 is to 1. So practice like this only. Okay. So assign Z equal to S equal to 2 tick B 0 0 question mark A S equal to 2 tick B 0 1 question mark B. This is not semicolon, okay, this is colon. Whether we are checking that it is true or false. If it is false, we are going here. It should be in straight line. I am writing like this. Or you can even write like this also in the Verilog editor. C, sorry. S is equal to 2 B 1 1 D. And module. So what this means? Basically, this means this is the number of bits and its base and the value. If I am writing B, it's denoting it as binary. If it is D, then it is decimal. If it is H, it is hexadecimal. And if it is O, it is octet. These all ways you can use. Okay. So this is the number of bits that S can store that we have to define here. Even if you are writing like this is also works. It will automatically truncate when we are writing like, for example, if it is 0 0 and say A is only 1 bit and we are writing this into this. So it will truncate and it will store A equal to 0. And if you are giving 0 1, it will truncate and A will store some other value, or maybe it will store 1. So if you are using the same size the both side, then it is not necessary to define this 2 or 3 or whatever size we are using. Here S is 2-bit, that's why I used 2 here. Okay. Then I am defining the value in binary. If I am using it is in decimal, you can directly write 0 or 1 or 2 or 3 like this. If it is hexadecimal also, you can write in 0, 1, 2. After 9 only, it will get A, B, C, D. Okay. You can directly write that. So the logic here, you understood the logic? Either you can write like this way or you can write like this.
Can you show the last code?
Sir, most commonly used.
Sorry, your voice is break. Can you repeat again?
Sir, I read which one is most commonly used in the industries?
Which one is commonly used in industries?
Yeah, which method is most preferred?
The method that
I read.
is also a part of discussion. Like whenever we have synthesizing this particular part into digital, like synthesis is basically when we are converting this Verilog into digital circuit, that code to diagram. This is basically synthesis is doing. So here we will be more dealing with NOT gate and AND gate, those things. Here we need an equality operator. So this is different gate. This is basically when we are dealing in hardware, this is a mux. So it depends on the hardware, like what are the resources we have available in that FPGA or whatever circuits we are going to design that chip have, then the utilization of uh, the hardware. Accordingly, we will design. So if you are available all these gates, then we will be designing with this. And if mux are more available, then we will go with this. Every conditional operator requires a mux. That's the basic thing. This question mark is basically a mux. This is a selection line and checking the selection, and it is true, then we are giving this. So with mux design, we are basically designing a mux itself. Using a mux, we are designing a mux. It doesn't make sense, but there will be a inbuilt kind of VRAM, then LUTs. These all things will be there. This LUT is basically what we are converting this mux to, and this LUT will be designed in the synthesis part. These all things will be more advanced kind of thing that we will be dealing in third session.
Okay, sir, clear.
So in EDA playground, I think you guys have been told with the EDA playground only. So this is our setup. So we will be dealing this in tomorrow's session. So we have two sections here. We have test bench and design. Our design part will be writing here, and we need to simulate that and need to check the functionality. For that functionality checking, we will be using our test bench code. Test bench code I will discuss tomorrow, and how to write that and all those things. We will be using Aldic as our tool. and EP wave as a simulator. So the EP wave will be get opened after the simulation of this Altic is open source. That's why we are using that. So one more thing, I will explain this when we are dealing with delays. That's the test time scale. We are dealing all the delays now in nanoseconds. That will be more useful when we are writing in test bench. So test bench is basically used for verification. Okay. At this particular time, we will be giving A equal to 0, B equal to 0. And after this second, we will be giving A equal to 1, B equal to 0. These things we will be giving in test bench part. In design part, we won't be giving any value directly. Like if you want to store some values in a variable, it requires a memory. So combinational circuits doesn't have memory, and when you are designing like that, it requires a memory. So that is not possible. So whenever we're designing a something in Verilog, you need to think parallelly about the hardware, whatever the hardware had been utilized, and uh, is it correct way of using the what resources? Whether we can further optimize the design, can we use less number of resources? Those things will be done when we are dealing with the Verilog design. So a design engineer is most uh, part thinking like how to optimize the entire code, how to reduce the resource. If resource utilization report, all those reports we will get after synthesis. So if resource utilization report is 70 or 75%, for example, okay. So further, if in the future we need to upgrade something on this particular design, like for example, if I am designing an AI detect camera, and now I am detecting only in an app. For that, I have utilized for 70%. If I want to detect a human being also, then I need to update the code entirely, or some part will be added, some part will be optimized. Then the utilization become more than that. So 100% of utilization is not optimized. We will be using around 30, 35%. We need to think about the future also, whether our design has what can be optimized in the future, or can add new parameters, or can add some other uh, means new technologies to that. These all things you need to be thinking when we are designing a big systems. These all thing even it not utilize around 10, max 10, more than 10 it is not going to utilize. These all are small systems. Okay, so in this we will be dealing with test bench and design part. So whatever we have done today, it is design part only. So we will be writing the module ports, and we will be defining the functionality of the ports, input or output or in out. Then we will be defining the functionality of module. We will be going for either data flow modeling or gate level modeling or behavioral modeling. We are not using switch level. Then we will be writing the test bench, and through the waveform diagram. Waveform diagram will be like this. I will go like if A I am giving 1 like this, 0, 1, 0, 1. A. At the time I am giving B like this, 0, 0, 1, 1. S. S will be 0, 1, 1, and 0. C will be 0 and 1. This is the expected simulation diagram of an half adder. when we have given, if the what, combination of A and B we are giving it as different, then this also will vary. How to give that combination and how to give the delay and how to generate that in EP wave, that whole thing we will be discussing tomorrow. Okay, any doubt in today's session? Today we have covered most of the basics you need for the combinational design. So we have covered, and after the with the data flow, and we have covered different level of modelings. Then 2x1 marks I have covered, then that in all the modeling. Then I have covered 4x1 marks in data flow modeling. Then given an idea how will be the simulation output. Any doubt? Any part I
Sir.
need to again explain? Tell me.
So just before you mentioned that we need a mux to like mux for defining conditional operator.
Yeah.
How is equality operator not defined using a mux?
If I'm saying like if A equal to 0, we need to check, right? So if it is not, then with this example only I will explain. Okay. So this S need to have will get the value of this, right? So when we are dealing in hardware, this value should be stored in somewhere. That's the first thing. Then whenever this is equivalent, then we need to go for A. Otherwise, we need to go for this. That's the thing I have explained somewhere. Yes. Is that 2x1x? Yeah. So here that case is there. If S is equal to 2B00, otherwise else part is this. If S, that selection part will be selected according to that S, then whether it is checking the true value at condition, whatever we are given the condition, if it is that, then we are giving it as to the output. Otherwise, we are giving it as the else part to the output. So for equality, basically we will be storing that, not as a mux. And we are converting this into our. So in the hardware, we will be having this port, and this thing should be there, right? So we will be storing this in somewhere inside the. We usually store all these values in a particular address registers, and that will be in a what microprocessor, and inside that a memory element will be there. In that the memory element we will be storing in the particular address, we will be having this value, this value, this value, and from there we will be calling that value and giving that into here. These many things will be happening inside that. So basically when we are dealing in combinational circuit, we won't be using this one. We will be using these operators only, but you can go for this also, but the utilization of the memory will be more here as compared to here.
The utilization will be more in the second one. Right?
Yeah, we will be having to store these all values. For comparison, we need to store all those values. So we will be using more memory. If I, that's what I am saying. If in the memory, if these values are already there, like without, if we have a big system and inside that we have a microprocessor and have a memory element, inside that we have that registers. If any of the registers have these values and a particular address is there, we can utilize this kind of coding instead of going for these operators. It will have to use this AND gate. That LUTs will be increased here. This is already there, then go for this. If it is not there, then we will be have to store these all elements in a particular memory. Then it will be using more memory required. Design part, this utilization and all those things you don't worry about now. You need to know how all varieties of coding we can do with the same design. Any doubts? Yeah, you can write Minnal. What is it? Sorry if I pronounce it the name wrong. Minnal. That S1, S2, you are defining it as separate instead of vector. That also you can write. No issue. I want to explain that vector concept. That's why I used single variable and defined it as 2. Any doubts?
No, sir, no doubts.
Okay, before next session, try to write the same code in behavioral modeling. So we will
Okay,
be
sir.
starting. We will be
Thank you,
starting with that, the same behavioral modeling in EDA playground, and we will be designing that the test bench also and doing the simulation.
Okay, thank you, Mr. Sangeet, for an incredible session on VLSI design. Your expertise has been truly enlightening. To all our participants, thank you for joining, and do join the remaining 2 sessions, which will be tomorrow and the day after. And certificates will be issued only after the completion of the 3 sessions. Once again, thank you for your enthusiasm and thought-provoking questions. We hope you gained valuable insights and will apply them in your own endeavors. Thank you all. Thank you for joining.
Thank you, everyone.
Thank you, sir. Thank you so much.
Thank you, sir.